Okay, so next topic that we are going to cover is the phase diagram. Okay, phase diagram or the full name is phase equilibrium diagram, but we only use this type of phase diagram at equilibrium, so we just omit the words equilibrium and we understand that it is a phase equilibrium diagram, right? A phase a phase diagram is like a tool for engineers to understand what phases are present at at different conditions, right? So um, and we will learn about those phase diagrams, how to use them, and how to interpret them. Right? But let's go back to the relationship between structure, property, and performance and application. Right. So we know that now we know that after like learning a little bit about structure, we know that metals can have different structures, and we can change those structures to influence the properties of that metal. And also we can not only change the structures, but we can change the defect within the structure to change the properties of our material, right? Um, the structure of steel would be a bit different from structure of brass or solder metal, right? And the property would be different as well, right? The strength, ductility, etc. So the performance would be different. So that's why you don't use steel as a solder material for electronic components, etc. And when we are choosing these material, whether it's steel, brass, or solder, how do we know which composition to use, right? How do we know which composition of steel to use for which application? For example, steel is an alloy of iron and carbon, right? How do we know how much iron, how much carbon we need to produce this type of steel that can be used to produce like car parts? Or how much copper do we need? How much zinc do we need to produce brass, right? Brass for the brass instruments, brass musical instruments, or brass fitting in plumbing network, right? And would the amount of copper and amount of zinc would be the same in these two applications, right? So in fact, they are completely different type of brass, right? The amount of copper and zinc, the composition is different in like musical instruments and plumbing works. And also when we are using solder, it's usually an alloy of lead and tin, right? Lead and tin. How do we choose the amount of lead, the amount of tin that we want to mix together to form the solder, right? Okay, so the composition of each of these alloys will influence the structure, and the structure will influence the property and the performance. So we have to know what type of performance we want to use, right? And for that performance or that application, we would have a property requirement. What is the strength for that application? What is the durability, ductility, hardness, toughness, etc.? All these strengths for that application. That's the requirement for material, right? And when we know the property requirement, we can decide on the structure that we want, because we know that structure can influence properties. And if we have a property requirement, then we can design a structure to have those type of properties. And to design that type of structure, we have to find the percents of like iron and carbon in this case, or copper and zinc in this case, or lead and tin in this case, right? That's why we need to use phase diagram, right? Because a phase diagram is a graphical representation of what equilibrium phases or equilibrium structures look like as a function of temperature, pressure, and composition. But because we are working at more or less at sea level, so we keep the pressure constant. So we are not really concerned about pressure. So we are really concerned about temperature and composition only, right? So we use a phase diagram to design an alloy, and we choose the composition of for that alloy for that application. Like in this picture here, we have the microstructure of copper aluminum alloys. Okay, copper aluminum alloys. When you mix copper and aluminum together, they form solid solution. Okay, solid solution of copper and aluminum. Whereas copper is the solvent atoms, and aluminum is the solute atom. Right? They form substitutional defect, and the strength of the copper aluminum alloy is a little bit higher than pure copper. Right? Well, how much higher? Depending on how much aluminum you put in there, and what's the microstructure that you get. Right? So when you mix copper and aluminum together, you can get two phases. You can get the alpha phase, like the lighter phase here, and you get the theta phase, the darker phase in this picture here, right? This is an example of a phase diagram for lead and tin. In fact, this is a phase diagram for the solder, right? And okay, so to produce a solder, what is one of the main requirement, one of the main criteria for solder metal? And the reason why lead and tin are used as solder materials for so long, and that's just like there's been a push maybe in the last 15-20 years to use lead-free solder, but lead-free solder is still quite expensive, more expensive than lead-tin solder alloy, and it's a little bit more difficult to produce as well, and more difficult to apply, unlike lead and tin solder. Okay, one of the main criteria or requirement for the solder is the melting point should be relatively quite low. Right? If you look at this phase diagram, you can see that the melting point of lead is quite low. The melting point of tin is also quite low, even lower than the melting point of lead. But if you mix lead and tin together at a specific composition, like 61.9% tin, you get really low melting point of 183 degrees Celsius, right? And that is really low. But why do we need low melting point for solder? Because our electronic circuit is really delicate. We don't want the chips, the IC or other electronic components to be exposed to high temperature for too long, right? Because you might damage it. Okay, so lead tin provide a perfect solder for electronics because the melting point is really low. Lead-free solder has melting point of about 300 degrees Celsius, right? So it's still a long way from lead tin solder. Okay, so when we produce lead and tin, we look at this when we want to produce solder, we look at this phase diagram, and we can see that at this composition, 61.9% tin, this has the lowest melting points of all the alloys. So we mix it at this composition and we use it as solder, right? So we have 61.9% tin, and the rest is lead, and that is our like perfect solder. If we don't consider that lead is toxic, tin is a little bit toxic as well, right? And you can see that in this phase diagram, you have the alpha phase, you have the beta phase, and you have the alpha plus beta phase, right? If you look at the phase diagram, right? You have the alpha phase, you have the beta phase on this side, you have the alpha plus beta phase. What are alpha phase? What are beta phase? So from previous slides, you can see that um, there are two phases in the copper and aluminum system, right? You have the alpha phase, theta phase, and they look different. Like one is darker, the other one is lighter, right? So that is for the copper and aluminum system. But when we're looking at the lead tin system, we can see that the alpha phase is on this left hand side of the phase diagram. The beta phase is on the right hand side of the phase diagram. So we can say that the alpha phase is the solid solution of PB or lead, right, with a little bit of tin, right? So if you look at the x-axis, it is composition weight percent tin, right? So these numbers represent the amount of tin in the alloys, right? So here you have 0% tin, here you have 20% tin, 80% lead, here you have 40% tin, 60% lead, etc., right? So on the left hand side of the phase diagram, you can see that it is closer to 0% tin, right? It's closer to 0% tin. So that means the phases that happens on the left hand side is mainly lead, right? So you have lead with a little bit of tin, right? So the alpha phase is a solid solution of lead with a little bit of tin. On the other hand, the beta phase is on the right hand side of the phase diagram, and you can see that this is the tin rich side. You have like 100% tin on the right hand side, right? So the beta phase is a solid solution of tin with a little bit of lead added in, right? And when you have lead and tin mixing together, you would get like both the alpha phase and beta phase, right? When you look at the microstructure, it will look something like this, but instead of alpha and theta, it will be alpha and beta, right? So a phase with a Greek letter as a symbol, that is a solid solution phase, right? A solid solution is when you mix two type of metal together, right? In this system, the alpha phase representing mostly lead with a little bit of tin. The beta phase representing mostly tin atoms with a little bit of lead mixing in there, right? And you can, and because the alpha phase is mostly lead and a little bit of tin, and the beta phase is mostly tin with a little bit of lead. Therefore, the structure is not exactly the same, right? The chemical composition is vastly different between the alpha phase and beta phase, right? The alpha phase mostly lead, a little bit of tin. Beta phase mostly tin, a little bit of lead. So the chemical composition of the alpha phase and the beta phase are different. The microstructure arrangement are different. So the properties should be different as well, right? So when you do the microstructure analysis, you grind it up, you polish it, and then you etch it. the grains will look a little bit different between the alpha phase and beta phase. In fact, that is what happened between the alpha phase and theta phase as well, right? The alpha phase might have more copper than aluminum, and the theta phase might have more aluminum than copper. So the two phases have different chemical composition. So the two phases have different properties, and one of that properties might be the reactivity to the etchants, right? The acid that you use to etch the surface. So you can see that the theta phase might react more with the etchants, so it gets darker, and the alpha phase might not react so much with the etchants, so it stays quite light. So you can see the difference in the phases when you etch the specimen, right? Okay, so alpha is a solid solution, beta is a solid solution, and these solid solution have a sort of solubility limits, right? You can see in this picture here, this number 18.3 on this side and 97.8 on this side. This is how much you can dissolve tin with in lead to get just the alpha phase, right? So this line here representing the solid solubility limit, or the limits of solubility of tin in lead. So if you add tin to lead with less amount than this line at this temperature, say for example, if you are looking at like 183 degrees Celsius, if you add in say 15% tin, you would get just the alpha phase, right? So if you add in 15% tin, because the limit is at 18.3%. But if you add in maybe 20%, 25% tin, you get the alpha phase, and the extra tin that you put in there will give you the tin rich phase, which is the beta phase. So you get this alpha plus beta phase, right? Okay, so when you have solid solution, the same with the liquid solution, you have solubility, or the limits that you can dissolve one thing in another. Like for example, if you want to dissolve sugar in water, you can only dissolve so much sugar in water at room temperature, right? Because you have reached the solubility limits of sugar in water. And if you want to dissolve more sugar in that water, you might have to heat it up. In fact, if you notice this line here, you will see the same thing, right? At low temperature, you have lower solubility limits. Say at closer to room temperature, right? The solubility limits of tin in lead to get the alpha phase is closer to maybe 3-4%, 5% by weight, right? And as you increase the temperature, you can see that the solubility limit increases as well. Just like when you are adding sugar to water, at low temperature, you can dissolve just a little bit of sugar until you get to the limit and you cannot dissolve any more sugar. When you heat it up, the solubility limit increases and you can dissolve more sugar. The same with solid solution, right? We'll come back to that a bit later. Okay, so this is an example of lead-tin phase diagram. This is an example of iron-carbon phase diagram, right? So we've come across a solid solution phase before, like alpha phase and beta phase. Like these are solid solution phase, and you have a Greek letter as a symbol for those solid solution phases, right? In the iron-carbon phase diagram system, apart from the solid solution phase, like the alpha phase, gamma phase, delta phase, right? Apart from these solid solution phases, like the alpha phase, gamma phase and delta phase up here, you also get this Fe3C, right? This is an intermetallic compound. Intermetallic compound is a compound that two metals or pseudo metals form when they join together. And because it is a compound, just like any chemical compound, you have a fixed ratio or fixed stoichiometric ratio between the two type of atoms. Right? For example, Fe3C, if you're looking at it from the weight percent, you will see that it is at 6.7 weight percent. Okay, but if you are looking at it as an atomic percent up here, right? Up here is the atomic percent of carbon. You can see that because the compound is Fe3C, you have 3 iron atoms and 1 carbon atom. Sorry. So in total, you have 4 atoms, right? 1 carbon atom and 3 iron atoms. So the carbon atom is exactly 25%, 25 atomic percent, right? 1 in 4, right? And the other 25%, those are the iron atoms, right? And because they are because this is an intermetallic compound, Fe3C, you have a fixed stoichiometric ratio of the two type of atoms. And because of that, you don't get a wide phase field, or you don't get solubility limit. You get just one line coming up from this point here, right? Remember, it is a fixed stoichiometric ratio between iron and carbon, right? Of 3 iron atom and 1 carbon atom. So 25% carbon, you get a line, like just a complete line here. You don't get a phase field, right? You don't get a phase region like other solid solution, like gamma in this case. In this area, this is called a phase field or a phase region, right? In this region, you get gamma, right? So you have a range of composition where you can get gamma, but for intermetallic compound, you don't get a range of composition. You get a fixed composition, right? So now we've encountered solid solution, we have encountered intermetallic compound, and you should be able to tell the difference between the two, right? The intermetallic compound for iron carbon system is really important. It's one of the reasons why steel is quite strong and why steel is widely used as engineering material, right? Or we'll come back to these different phases a bit later on, right? So if you're if you're looking at this phase diagram of steel, you will see that there are many phases, and they look like the phase diagram look really busy, right? Compared to the phase diagram of like lead and tin, right? Lead and tin phase diagram looks quite simple. You have the lead rich phase alpha, tin rich phase beta, and you have the mixture of the two. You have the molten metal, the liquid metal, or you have the liquid plus alpha and liquid plus beta, etc. So it's quite simple, but when you're looking at the iron carbon phase diagram, it's a bit more involved, a bit more complex. Luckily, as engineers, we are concerning ourselves with this corner of the phase diagram, because this is the steel's corner of the phase diagram, right? And a little bit around this range, this is the cast iron corner of the phase diagram. Okay, so we'll come back to phase diagram of steel in a little bit.